Okay, so we're now past the 0th law of thermodynamics. We're going to do the first law of thermodynamics. And so there's a bunch of different ways these thermodynamic laws have been stated. This one's more stable than the second and third law, so we'll get into some controversy later. So this is a general statement of the first law of thermodynamics. The internal energy of an isolated system is constant. Okay. And so there's a lot of words in this particular thing. We have to learn about system. What is system? What does isolated mean? Of course, internal energy. We've talked about internal energy. That's U of USHAG. And then in terms of changes, right, we know that energy changes, but how does it change and what's constant? What can we use this law to do? So we're going to explore different ways of stating this first law and different ways to use it mathematically. Okay. And in doing so, we're going to get into heat and work and enthalpy and heat capacity and all these different state functions. So, and once again, heat is Q, not the partition function. So this is system and surroundings. Let's talk about an isolated system. It's over here on the right, where matter and energy can't leave. So if you've got a system that's isolated, you've got a lid on it, and it's insulated. So you can't have energy go in or out, and you can't let matter go in or out. And so that's an isolated system. If you have a closed system, matter can't leave, but energy can leave. So that's a closed system, something that's capped, but has conductive walls, heat conductive walls. So like a metal container, not very insulating. And then you have an open system, like an open beaker where matter can leave and energy can leave. Now, what's interesting about this is we can do a lot of things with our brains, conceptually, okay? We can take an open system, like boiling water in a beaker, and it's open to the top, but conceptually we can draw like an imaginary line over the gaseous products that leave and sort of mathematically treat it as a closed system. Even though it's open to the atmosphere, if we want to say what was the expansion work done, we've produced 3 moles of gas and pushed back the atmosphere. Have we really? Not really. But we draw an imaginary balloon over the top and we say how much work was done by the gas pushing out against the atmosphere. So we can calculate that as a closed system, even though in truth it's an open system. But we can, like I said, draw these boundaries conceptually and do the math. And so we do that a lot. A lot of times our systems are the chemical reaction. So we have reactants, products, the arrows, and that's our system. And so if it produces a gas, we're drawing an imaginary line around that gas. So when it goes out in the atmosphere, we're still keeping it in our system, even though it's out there. And energy goes out of the system into the surroundings, and so it has a negative value to show that it's exothermic, say, if we have heat leave. So because it's negative, our system is the equation. Negative energy means the equation lost energy. So it's exothermic. That energy went into the surroundings. Okay. Now, the surroundings are sort of uncontrolled, right? They go into the room. They increase the heat of the atmosphere around it, or the whatever the container is. And we lose track of that energy. We can calculate how much went in or how much came out of the system, but we kind of lose track of that. It just goes into the surroundings. But we could treat also the universe as a closed system. We don't have any way of knowing. I mean, I've got kind of a fuzzy boundary there. We don't know if matter can leave the universe or if energy can leave the universe. So we, at this point, just have a conceptual thing that the universe is an isolated system, that we have no knowledge of the ability of energy or mass or matter to leave the universe, and it's expanding space anyway, so it's growing in size, but into what is a question science can't answer or hasn't answered yet. Like, what does that mean? What is outside the universe? It's that's the kind of question that breaks us right now. We don't really know the answer to that, so that's kind of cool. So if we have things like cooling steam, a mole of steam cooling from 373 to 298, how is it cooling down? Well, heat's leaving the system, and so we have a negative value on that because the system is steam, And as it cools down, the heat's leaving, so that heat is lost from the steam, that's our system, to the surroundings. And so Q would be indicating the heat. So we see this change. And so how much energy went into the surroundings? Okay, we change the sign of that. If it came from the system, the surroundings is the opposite sign. So it's a positive 1870. So we don't lose any energy. If it left the system, it went to the surroundings. Reason I show you this is if you see here down, surroundings, Q surroundings equals minus the Q system. So the heat going into the surroundings is the heat from the system. This minus sign right here, a lot of times people make the mistake of thinking they've already used that minus sign. We've got a negative amount of heat here, right? But no, this minus sign is not that one right there. It's this one right here. Do you see what I'm saying? So it's if you've got a negative heat value for the system, you change that sign and now the surroundings are positive. If you had a positive value for the system, so it took in heat from the surroundings, you change the sign and the surroundings lost energy. The energy went from the surroundings to the system. And so minus signs are your enemy or your best friend, however you want to think about it, but that's where most of the mistakes come. Units are a big deal, and in this now thermodynamics, it's the minus sign. So that tells you where the heat's going, where the work's going. So, so pay attention to your signs. So this first law of the internal energy of an isolated system is constant. Another way to say that is energy is neither created nor destroyed. Remember that energy is also matter, right, with Einstein's equation that we used last time. And so sometimes you'll hear mass energy is conserved. Sometimes you'll see hear mass is conserved, but mass can be turned into energy. So they'll say the mass energy of the universe is constant. That's another way to say it. And that's treating the universe as an isolated system. So energy doesn't leave, mass doesn't leave. So the mass energy of the universe is constant. The thing that does change over time is the usability of that energy. And that's where entropy is growing as we go through time. And some would say that that's how we measure time, is by the change in entropy. So that's kind of weird to think about. There's a lot of philosophical concepts in thermodynamics. So energy is the system's capacity to do work. So this is the main idea. I mean, have you thought about what energy is? I mean, it's really not tangible, right? We measure temperature, and we say when two things are in contact with each other, they share a property, and we call that property temperature, okay? And they're exchanging energy, but what is energy? Well, this is the best definition that we've come up with, and it's a capacity to do work. So if you have lots of energy, you have a lot of capacity to do work, and if you have less, you have less. So what is a compressor? Like a compressor is compressing gas into a tank, and now we've increased its energy because it has the capacity to do work. We can drive an air wrench with it, or we can do all kinds of things. But I like air wrenches. Obviously, they're doing work. They're tightening the lug nuts on your wheels. That if you go to Discount Tire, and that's an air wrench, and it's pretty good, isn't it? So that's you compress that air into a small space, and you've increased its energy. It has a lot of capacity to do work, and then we can see the work done. And then, of course, when you do work on that gas, you're increasing its energy. You're increasing its ability to do work. Tightening a spring, compressing a gas, these are all very familiar ways to store energy. Okay. Now then when the system does energy or loses energy, it's doing work, it loses energy, right? So when they run that air through the air wrench, it's torquing on the lug nuts, and then it's coming out the backside, and the excess energy, or it's used energy to turn the nut, and then it's just lost to the surroundings. So perfect use of work, which is impossible, would be you have the compressed air, you turn the lug nuts, and the air comes out with no kinetic energy. You've used every bit of the kinetic energy of that air. Well, that's not possible. We can get a lot of air, we can get a lot of work out of it, but it's still coming out of that air wrench with a fair bit of velocity. But that difference in speeds, again, you could use temperature to measure that. So that's going to be your primary measure of efficiency, is the temperature difference. Okay, so we could follow the amount of energy something has by following its temperature. And when you compress that gas, that heats up. That's why there's little cooling fins on the compression line where it goes into the tank. And if you grab that, it'll burn you. Okay, the system can also gain or lose energy in the form of heat, which would be a Q. We do have to choose our words carefully. I will try not to let you get sloppy with the way you speak, and I'll try to be precise as well. The system gains and loses energy. It doesn't gain or lose work. It does work. See what I'm saying? It loses energy or uses energy to do work or to generate heat. It doesn't gain or lose heat. Okay? Heat and work are ways of changing energy. So they're ways of changing. It's kind of like cash or credit, right? The energy is your money in your account. It's your capacity to do work. You got more money, you got more capacity to do work, okay? How you do that work, let's say credit is work and cash is heat, okay? So you could go and do a transaction where you pay half the bill with your credit card and the other half with cash. And now you're at 50% efficiency because half of the transaction was credit, and they were calling that work. And the other half was cash, and that was heat. If you want a more efficient process, you take 75% of the bill, pay with credit. That's your work piece. And then your heat piece is only 25%. And that's a 75% efficient process. So so heat and work are transactions. And so if you lose 100 joules of energy, you could lose it all to heat. You could lose half to heat and half to work. You just can't get all the work. All of it can't be work. Heat is the enemy of our efficiencies. Yeah. So this is kind of what we're talking about. Work is that fundamental property in thermodynamics because it's measurable. We can raise a mass against a force. We can run a current against a resistance. All of these different things are different forms of work. We could expand a gas or compress a gas. So you can measure the pressure change, measure temperature changes, and things like that. And so again, you can raise a weight, expand a gas, drive current through a resistance. All of these are very easy then to calculate the amount of work that was done. So the surroundings kind of decide whether some process is heat or work. So if you have the system delivering energy to the surroundings, and the surroundings are taking that energy in terms of random motion, we would call that heat. So you look at the surroundings, you say, okay, this energy is coming out of my system and it's coming out as heat because it's creating random motion. Or if it's coming out of the system and pushing the surroundings in a particular ordered direction, then it's work. So think of a piston, right? So the piston is moving in a particular direction, and so it's doing work by moving all of those atoms in the same direction. So that's work. If it's expanding, even in a balloon, it's expanding in all directions. It's still expanding out, okay, which isn't random. So it's doing work by expanding, by pushing everything out. Okay. So ordered motion, disordered motion, that's, another way of thinking about work and heat. So here's the first law in action. Let's look at some of the mathematics. So this is, the total energy is that change in the system and change in surroundings. And this is the shortest version of the first law, that the total energy is zero. Okay, the change in total energy. So when I said the mass energy of the universe is constant, okay, then the change in mass energy is zero. It's another way to say it. So that just means that the system and the surroundings are opposite signs. So one of those is negative, right? If it's the surroundings is negative, you change the sign and you get a positive change in the system. If the system's negative, then you change that sign of the surroundings and it becomes negative too. So mathematically, this is a way that you can state that first law as well. So without electrical, chemical, or phase changes, there's only heat and expansion work. This makes things a lot easier. And so then we have this here. This is one of the key equations for the course. So the change in the system, and so we focus because, like I said, we draw our chemical reaction. That's typically our system that we're looking at. Everything else is the surroundings. So we have a reaction taking place in a beaker. The beaker is the surroundings. The atmosphere is the surroundings. We're just looking at the reaction. And so we look at the heat of reaction and the expansion work of the reaction, and we get Q and W, we add those together, and we get the change in energy of the system. And so we have this internal energy. We talk about state functions. Let's think about state functions. The nice thing about state functions are that it doesn't depend upon how the system was prepared. And so let's think about potential energy. If you're standing on the second floor, your energy is fixed by your mass and the force of gravity acting on you, right? Potential energy. And it doesn't matter if you came down from the third floor or up from the first floor. Does everybody agree with that? Yeah, internal energy is the same way. So if I got to this particular pressure by compression, so we compressed a gas to get to that pressure, or if we expanded a gas to get to that pressure, whatever pressure I have a certain amount of energy. Whatever volume I have, however many number of moles in there, whatever temperature I'm at. So it doesn't matter if I got to that P, V, T, and N state by compression or cooling or heating or whatever. If I know those state variables, I can calculate the energy, right? And we did that with the equipartition, right? It was the number of moles times 3/2 RT for argon. And it didn't matter if I cooled it down to get to that energy or heated it up to get to that energy. So that's what we mean by state functions. And the nice thing about state functions, since it's path independent, you don't have to do the integration to get here or there. You just need to know final minus initial. So if you want to know the changes using state functions, you just take the final state, subtract the initial state, and you've got the delta. So that's really the main point of why we like these state functions. Heat and work, however, are not state functions. They are path dependent. And so I could have gotten to this energy by releasing all heat and losing all of that energy in form of random motion for heat, or I could have done quite a bit of work and lost very little heat and got to this energy. So the path that I take could involve more or less work. And you can kind of think about that with the stairs. If I go upstairs, it's a different path. There's a different work-heat ratio than if I took the elevator, okay, or slid down a slide from the third floor. Okay, so there's lots of ways to change the state, but the states themselves can be subtracted and find the deltas. But for work and heat, you've actually got to know the path. Okay. So let's talk about expansion and moving pistons. So if we have pressure here and we've got this piston, this very simplified piston, it's just a disc in a cylinder here. We've got an external pressure here, and we have a pressure inside. So here's our system, and it's pushing on that piston, and it moves at a certain distance, dz. Okay, so we have the area of the piston times the displacement, or the stroke length. And that gives a volume. So this volume here is going to be the amount of this, V final minus V initial. So you have the displacement volume. So this is why we talk about these things in our automobiles, right? Our pistons are all sweeping through a particular volume. They have a particular area. And so we talk about the displacement volume inside an engine. And that, again, relates to the amount of work it can do. So we have, a 5.7 liter engine or a 1 liter engine. So a 5.7 liter engine is going to be able to do more work because it's pushing more volume. So when this piston of area A moves through a distance dz, it sweeps out this volume dv, and the external pressure is equivalent to a weight pressing on the piston. So that's the force, right? The force is that weight times that area, and so then we have that equation where then we can calculate the amount of force, and then the distance will give us the energy. So here's our indicator diagram. And so we have this external pressure here, and we have a V final and V initial. So a system pushes a piston back against a constant external pressure. And that area under this curve of the indicator diagram is equal to the absolute value of the work performed by the system. So here's our equation for work, for expansion work. And so the negative sign is indicating from the view of the system. Okay, so from the view of the system, that's where we get this negative sign. And notice it's V final minus initial. This is one of the places where people make simple mistakes. It's just our own mental bias to want positive numbers. At least some people. I don't know if everybody suffers from this bias. But a lot of times when calculating their work, they'll take the big volume and subtract the little volume. But that's not what it says. It's final volume minus initial. Sometimes the final volume is smaller. And if the final volume is smaller, then you have compression. Okay. And if the final volume is bigger, you have expansion. So be sure to pay attention when it says F and I, right? Final minus initial, so that you get your signs correct. So in this case, our initial is small and our final is big, so we're doing expansion. The opposite would be compression. So a lot of times on these diagrams, these PV diagrams, we'll have arrows on the lines. And so there'll be a little arrow on this line showing you the direction that it's going. So you got to pay attention. If you're looking at this thing and you see that tiny little triangle on there, it's telling you that you're going in this direction. It's telling you that it's an expansion. And so then this would be your V final and your V initial. And so that means that the difference here is positive times the external pressure. Change the sign. That means the work is negative. Work is negative means the system's doing work on the surroundings and losing energy in the process. Okay. There's a different kind of expansion. There's reversible isothermal expansion. And so here, this is a curved line, and its arrow would look like this. So you'd see this little arrow on the line, and so they're saying, okay, it's expanding. Notice the previous example was expansion against a constant external pressure. So this is what we got with the expansion against a constant pressure. That was the amount of work that we got. And notice for this isothermal reversible process, we get a little bit more. We get a little triangle more. So that little extra area there is a little more work that we get out of it. Now this is held at a constant temperature, so this requires some sort of thermal, I call it thermal ballast, or a ballast in a ship is like a mass at the bottom of the ship to keep it upright. Okay, it sort of stabilizes things, and for a thermal ballast is an object that has a lot of heat capacity. So it doesn't want to change temperature. So like if you put your reaction in a cooling bath or a heating bath, that cooling or heating bath is there just for temperature. It's a thermal ballast. It's not mass, it's heat that is able to flow into the system, or sink heat. If your reaction generates heat, it's going to go into the bath and not raise the temperature of your system. It's going to just keep it at a constant temperature. So that's what we mean by thermal ballast. And so this reversible expansion is kind of slowish. If it happens too fast, it becomes adiabatic. And so it takes a little bit of time for that heat to flow in and out of the system. So sometimes these are idealized systems. They're not exactly achievable. Okay, but they'll give us the maximum amount of work. So let's look at this if we can figure this out. We have this change in work. Since we've got this smooth curve, we want to integrate it. So we have this change in work is equal to this pressure right here. We're going to start here, and we're going to just change it by a tiny little volume. We're going to calculate this amount of work here. And so we're going to integrate both sides. Well, the integral of dW is W. Okay. And so then we're going to integrate this with respect to volume. But we know that the pressure depends upon the volume. So if I expand that volume, then my pressure is going to drop. So we can take this and put in nRT over V. And so now we have the volume. So the nRT comes out front, and we have the integral of dV over V. It looks a lot like that derivative of the natural log. Okay, and so then we end up with the natural log of V final over V initial. So it was natural log of V final minus the natural log of V initial after we did the integration, but the minus sign inside the logs can make a fraction. And so this is what we have. This is the equation for reversible isothermal expansion. So we've only been through 2 slides talking about work, and we already have 2 equations for the work. It's path dependent. So you got to know what the context is. Is it against a constant pressure, or is it isothermal expansion? So in all of these situations, you've got to really understand, what am I talking about with this change? And so you're going to have lots of equations on your note card for the different conditions. And so this would be, again, reversible isothermal expansion. That's what you associate with this equation down here. Notice it gives a little bit more work, okay, because it has that triangle up there. So let's go ahead and do a top hat on this. Let me go back and make sure. Yeah, it's working. Okay. Just a few more, a couple more, 2, 1. All right, very good. And so these questions are basically what I just said, but it's a kind of a check to see if you're listening, right? So yeah, reversible isothermal expansion does more work for the same change in volume, because we get that triangle at the top that we miss if it's just a constant pressure. Okay. All right, so let's go back.
When you say triangle at the top, you're talking about when you take the integral. It's the
Yeah, so I'll point it out again. Yeah, so this little triangle at the top is the extra amount of work that you get. Because here is it, this external pressure here is listed, and it just cuts right across. Okay. So let's do some other simple practice. So calculate the expansion work when 55.8 grams of iron reacts with hydrochloric acid to produce hydrogen gas in a closed vessel of fixed volume. Now this is a very common question, this type of question on the chemistry exams, or like the chemistry GRE, if you're going to do that. Fewer people are taking it, but if you do take it, this is one of the ones that you'll most likely come across, because you don't need to do any work. Like there's no calculation involved here. Why not? What is it? What is the expansion work done in a closed vessel of fixed volume? What's V final? And the same as V initial, right? So no matter which equation you use, whether it's delta V, which would be 0, no work, or the natural log of VF over VI is the natural log of 1, also 0. It doesn't matter what equation. If you put in delta V equals 0, you're going to get 0 work. But you don't even have to do that. You can't do expansion work if you can't expand. So this is a trick question. Part A is a trick question. You have this whole thing with all kinds of numbers and everything like that. What's the expansion work done here? 0. If there's no expansion, there's no expansion work. If there's compression, no, there's no compression either. So we can't change the volume. We can't do expansion work or compression work. Okay, now an open beaker at 300 Kelvin. All right, so we put iron in, we drop in aqueous HCl, it generates hydrogen gas, it leaves the beaker. How do we capture that work? Well, it's not asking you how you capture the work, it's asking you just how to calculate the work. So here's where we draw our imaginary balloon surface over that H2 gas, and we calculate how much volume it takes up once it's generated. So so let's go through this. 55.8 grams of iron. We look at the periodic table, and since I'm writing the problem, I made it easy. It says it's 55.8 grams of iron per mole. Okay, so I don't have to do any calculations. All right, and then we look at this reaction, and we get 1 mole of H2 gas. Let's put Fe over here. Per mole of Fe. And so this amount, if we run this reaction all the way to completion, will generate 1 mole of H2. What do I do with that number? Remember okay, first of all, let's think about this. This is against an open beaker, or it's in an open beaker, and it's expanding into the room. Okay, what's the pressure? Is the pressure something that changes as it expands, or is it constant? We're only generating 1 more mole of H2 gas in the atmosphere of the Earth. Yeah, that's right. It's constant, right? We're not changing the atmospheric pressure by generating 1 more mole of gas. So it's a constant pressure situation. So our work is equal to minus P external delta V. So that's the equation we want. So this P external is going to be an atmosphere. This is V final minus V initial. So we need to come up with V final and V initial. What is V initial? Nothing, right? Because we didn't have any hydrogen gas when we started. So V initial is 0 liters. Does that make sense? We don't have any hydrogen to begin with, so it should be 0 liters. What about V final? We've got 1 mole of hydrogen gas now that's been generated, and so we just need to use the ideal gas law to figure out what our volume is for V final. Okay, so V final, I'll go ahead and do the algebra. PV equals nRT, so just bring P on the other side. 1 mole. Let's hold off on the gas constant. We do our temperatures in Kelvin. This is 300 Kelvin. Pressure, 1 atmosphere. Which gas constant do you want to use? Yeah, the one with liters and atmospheres. Okay, good. 0.08206 liters, atmospheres per mole Kelvin. Okay, very good. It's something like 24 liters. Does anybody have it?
24.6.
Okay, 0.6 liters. Okay, so that's our V final. Okay. So work is equal to minus 1 atmosphere times 24.6 liters. So it's 24.6 liter atmospheres. That's not very fun, is it? Because, oh, negative. Thank you very much. Boy, James for the win. I have these here. For the case of this exact situation, yes. You can put it on your phone or whatever. Nice.
Thank you, sir.
Lest you think I get annoyed if you correct a mistake of mine, I'm proving to you that I'm not annoyed by that. These are okay. So very good. Negative. But now but that's not very satisfying to me to have a change in energy, right? This is work that I've done. How much work have you done? 24.6 liter atmospheres. Well, what the heck is that? Yeah, you know? So how do we get out of liter atmospheres and into something that I'm expecting like joules? Yeah. There's a nice little trick here, okay? So minus 24.6 liter atmospheres. And where have I seen that before, right? I want some kind of conversion so that I end up with joules in the end. Where have I seen liter atmospheres before? Like times each other, liter times. It's on the screen. Yeah, and look right here, I see this. Liter atmosphere. So what if I put down here 0.08206 liters atmospheres per mole Kelvin? Okay. Now where have I seen mole Kelvin before? Huh? The other gas constant? The other R? 8.314 joules per mole Kelvin. So if I have my two gas constants memorized, I can turn them into a conversion factor because R is R. They're equal to each other. So my mole Kelvins cancel and my liter atmospheres cancel, and I've got joules. That's what I like. And this is, if you do this division, you'll see maybe you'll recognize this number, 101.325. Okay. And that's the joule per liter atmosphere. And what it really is that's the amount of pascals you have in an atmosphere, like kilopascals to atmosphere. So this is converting that pressure unit and volume unit and everything. But this is a nice trick, okay? And so I just need to multiply this by 100, basically. So 2460 joules minus. So that's how much work was done by this reaction, pushing back the atmosphere. Isn't that cool? Yeah, that's always fun to see. Everybody's like, what? I can just use the gas laws just to... And so then we get into calorimetry. We're running out of time, so we're going to have to pick this up next time on the calorimetry equations. But that's good because Monday's lab is on calorimetry. We're going to get started on that. So let me just focus on this real quick before we leave. This is a bomb calorimeter, and that's what we're going to do, not next week, but in the week, 2 weeks after that. So you put your sample in here. So you have your fuel in here. It can be like a starch. We do have Crisco, so we can look at the caloric content of fat, the caloric content of starch. If we found like a pure protein sample, we could put that in there and get the caloric content of protein, and we could compare it to the labels on the back of the things, and they would match. That's kind of cool. So you put, a little daub of Crisco in here and fill this up with O2 and seal it up, put it inside this water tank. We've got a thermometer here. We've got a little spinny vane motor that circulates the water. And we've got these leads, and we have a little piece of wire in here, and we hit the electrical current. The wire heats up, and boom, it burns inside this bomb. And the volume does not expand. So there's no work done. It's only heat. So the change in the system, this reaction generates heat, and the heat goes into the water. The water goes up by a certain amount of degrees, and then you back calculate how much heat came out of your little sample here. You even have to account for how much wire burned, because again, the wire is in oxygen too. So you weigh the wire, you build the bomb, you detonate it, you pick the wire bits out of the inside of the bomb and weigh them again. So you know how much of the wire burned and how much your sample burned, and you take track of the heat. And a lot of this is more like accounting than chemistry. So you got little categories. There's a bit from the heat from the wire, heat from my sample, and all of that. You can also put a heater in here, and that's what we'll do on Monday and Wednesday, is change, we'll put a heater in there, and we'll look at the calorimeter constant and try to get the heat capacity of water as well. The one thing, though, if I could get everybody's eyeballs on me, is we're going to be using a resistive heater, and it has to stay in contact with the water if it's powered. Okay, I tried this 10 years ago. I bought this immersive heater, and the students burned it out in the first 30 minutes. Like the first student pulled it out, and then it burned up. If you pull that heater out of the water with the power on, it's done. Okay, so you have we'll have a power strip. So you punch off on the power strip, then pull it out, and everybody's good. Okay, so please don't burn up my heaters. So anyway. They're not that expensive, but, we want the people behind you to be able to use it too. So, all right. So we'll pick up here next time.